Everybody, can you hear me?
Yes, sir. Good
Am
morning.
I audible? Okay, so let us start. Is the slide visible to you all?
Yes, sir.
Yes. Okay, fine. So yesterday we have done some problem on this KVL. We have got some ample idea about KVL and KCL. Now today
Share
we'll
the screen
start with
first.
electrical
Do you
measuring
have
instrument.
any other?
And over there, the
Wait,
two
wait.
most important
Before
one
we
are the
get
ammeter and
started.
voltmeter.
But the foremost
Obviously, you have got
step
some
is
idea because the
audience
last
analysis.
chapter itself I have given
So
some
when you
idea
get
to
to
you. We will
analyze your
continue with the
audience, you
same
need
idea,
some
but over
depth
here
into your
we
speech.
will try to learn
This
how
is the
these
collector.
ammeters and
They may be
voltmeters
mixed
can be
in
modified
general, like there are
so
few
as to
use and
extend their range. But before that, let us just have a recap of what we have studied in the last class. So, as we all know that an ammeter is a electrical instrument which is going to measure a current. This ammeter is always connected in series between the source and the load so that the current to the load passes through this ammeter and thereby it is going to measure it. Usually an ideal emitter, okay, then an ideal emitter is going to have zero resistance. And why it is going to be zero resistance? Because it should not affect the measurement of the current in the circuit. So ideally an emitter should have a zero resistance. But the truth is that no emitter is ideal in nature. All the emitters in our engineering world are always going to have some sort of finite resistance. That means their resistance is going to be very close to zero, but they are never equal to zero. Why? Because obviously an
Represent. Are and audience analysis. You don't have to personally go and inquire what by looking at people, by listening social status and their education. I think we'll continue with this in the next class also. So Deep, please remind me that we were in inference in the next class. Will you be I think we'll continue with this in the next class also. So Deep, please remind me that we were in inference in the next class. I think we'll continue with this in the next class also. So Deep, please remind me that we were in inference.
coil, the other end of the coil is connected to the load. So in this way, the current is actually going to flow through this coil. And in the process, what happens? You all know that when current passes through a conductor which is placed inside a magnetic field, then it is going to experience some sort of movement. Okay, so a conductor placed inside a magnetic field is definitely going to face some sort of movement, and this movement can be utilized to run or move this pointer. And the best part is that if the amount of current or the movement of this particular pointer over this graduated scale is going to be proportional to the amount of the current flowing through the coil. That means if the number of or the amount of current is going to be low, then obviously the angle of deflection by this pointer is going to be low and it is going to show you low value of current. Similarly, if the value of the current is large, then obviously the angle by which the pointer is going to be deflected is going to be high. And in this way, it is going to show you a higher reading of the current on the graduated scale. So this is basically the idea behind the working of an ammeter. Now let us move on to the main part in this chapter, that is the extension of ammeter range. Now, obviously, every year some question used to come on the extension of either an ammeter or a voltmeter. So, alternatively, questions used to come. So, please be very serious about it. Now, the concept is extension of ammeter range. Now, let us say that I am having a ammeter. So, this is one ammeter, and this ammeter is capable of measuring a maximum current of 5 amps, let us say. Now over here, the least current that it can measure is over here on this graduated scale, and it is at 0 ampere. Similarly, the maximum current that it can measure, let us say, is 5 ampere. Now, suppose I want to increase the value of this maximum current to be measured. It is known as extension of the range. So here the range is actually 0 to 5 ampere. Now I want to increase the value of this range to, let us say, from 0 to 50 ampere. That means the same ammeter can be modified to measure a extended range of the current. From 5 ampere, we can make it to measure a current higher than that. So let us say the current that it can measure is now extended to 50 ampere. Now, how or what modification should we make in the existing ammeter so that the range is going to be extended? For this purpose, what we usually do is to connect a shunt resistance in parallel across the coil of the ammeter. Now, obviously, in this case where I have not done any sort of modification, this ammeter is originally designed to measure a current in the range from 0 to 5 ampere. So when this current I is flowing, and this current is going to flow through this coil of the ammeter. Let us say this coil of the ammeter is having a resistance, very small resistance. Let us say it is RC. This resistance is known as the resistance of the ammeter coil. Now, suppose I want to increase the extension, or I want to increase the maximum current that this particular existing ammeter can measure, then what we need to do is that we need to connect another resistance in parallel across this coil RC. And that resistance is usually known as a shunt resistance, or simply we can say, tell that it is a shunt. So if a shunt is connected across a ammeter coil, then always remember that we have actually extended the range of the ammeter. So nowadays, since the laboratory is closed, therefore I cannot show you. But if by chance the laboratories get opened up and I can make a video, then obviously I will show you the construction of the ammeters. And in those cases, I can show you how a shunt is actually connected in parallel across the ammeter. So that is a different case. If good times visit us, then obviously I will be able to show you. But at least remember that whenever I want to extend the range of the ammeter, what I need to do is that I need to connect a parallel resistance, a resistance known as shunt, in parallel across the coil of the ammeter. Now, what is actually going to happen if I am connecting this shunt across this ammeter coil? How the range is going to be extended, that we will see right now. So this is a very simple mathematical derivation, and this derivation is going to help us in finding how we can extend the range of the ammeter. Now let us say that RC is the resistance of the ammeter coil, and let us say RSH is the resistance of the shunt. Okay, that we are going to connect in parallel across this ammeter coil. Let us say that I, capital I, is equal to the full scale ammeter reading current. What does that mean? That means previous thing, or before the modification, let us say the full scale of this ammeter was from 0 to 5 ampere. So 5 ampere is the full scale ammeter reading of this ammeter. That means here in this case your I is equal to 5 amps. Now suppose I want to extend the range to 50 ampere, then your IM is equal to 50 ampere. That means it is the extended value of the current that we need to measure. Now, if you will see that in this case, the potential difference across the ammeter is equal to the current multiplied with that of this ammeter coil, and this is equal to IRC. Now, similarly, in the second case where we have made the modification by connecting this shunt in parallel to extend the range, over here also the potential difference across the same ammeter coil should be same. Why? Because this ammeter coil resistance is not going to change, and moreover it is designed in such a way that the insulation over this ammeter coil is fixed for a voltage. For example, over here the potential drop is again going to be equal to I into RC. But as you can see, I have already connected a shunt in parallel across this ammeter coil. Now, if the extended current, that is IM, is going to flow, then remember, as usual, whatever was the rating of the ammeter coil, that amount of current will be definitely flowing through it. So it is the same I, but whatever extra current we have applied, that is in this case I was equal to 5, but now I have extended the range to 50 ampere. So naturally 45 ampere more current I am going to measure. So in this case, the rest of the current, that is 45 ampere, is actually going to pass through this shunt resistance. So in this way, we can say the potential, as you can see directly that these two are in parallel with each other. Therefore, the potential drop is also going to remain the same. So in other words, I can say your IRC must be equal to IM minus IRSH. Now, since we are interested to find the value of the shunt that we require to increase the range of the ammeter, for that, by some mathematical manipulation, we derive that your ISH is equal to RC multiplied with I divided by IM minus I. So in this way, or this is the expression for the shunt resistance that we need to connect across a normal ammeter if I want to extend the range to IM from the value of I. So this is a very simple thing. Simple logic is behind it. Now I hope everybody have understood. Is there anyone who can't understand? Yes, anybody? Yes, please respond.
Sir, understood.
Have you understood?
Yes, sir.
Okay, thank you. Now let us do a small problem. I will not solve this problem because this problem is a very easy problem. I am giving you 2 minutes of time. Please solve this problem. The question is, what shunt resistance is to be connected to make this 1 milliampere 20 ohm meter described in the described over here into an ammeter with a range from 0 to 50 milliamps. So here the normal current of this ammeter is 1 milliampere. I want to extend the range to 50 milliampere, and the resistance of the coil of the ammeter is 20 ohms. Now quickly find out the method by which I can increase the range of this ammeter to 50 milliamp. Please do it within 2 minutes. I am waiting. Please do it. It is the put the formula, get the answer type. Very easy to do. So this is the formula. So we'll use this formula over here.
Sir,
So
0.4 ohm.
no, please be very sure that it should be up to 3 decimals because it is a very small resistance. You are correct, but please,
0.
yes,
0.408.
408.
0.408
0.408.
ohms. Okay, so always write it in this manner that the short resistance is equal to 0.408 and it must be connected in parallel across the shunt, across the ammeter coil. So this is how you have to draw the next diagram and show it. So all of you who have answered it correctly, thank you. Now if anybody is having any problem, I don't think anybody will be having any sort of problem, because this is quite a very simple one. So nothing more to discuss about it. Now let us move on to the next chapter. That is for voltmeter. Now let us talk about the voltmeter. Now usually what happens, we design the coil. Now what we need to do is that, okay, so we will talk about the voltmeter. So again we will repeat all those things that we have already covered. Superficial idea I will give you. So a voltmeter is a electrical instrument that is used to measure the electrical voltage or the potential difference across either a circuit source or a load, or rather I will say across a circuit element. A voltmeter is always connected in parallel across the circuit element. Okay. Ideally, a voltmeter or ideal voltmeter must have infinite resistance, but the truth is that it is never so. Real voltmeters do have some very high resistance, but of course it is not infinite. Now, why it should be very high? Because as you can see in this diagram, that if the voltmeter is connected across the circuit element in parallel, so there are two parallel paths for the current to flow. So some amount of current will flow through the circuit element and some of the amount of current will flow through the voltmeter. Now if the resistance of the voltmeter is not very high, then a lot of current is going to flow through it, and obviously the drop will be across the resistance of the voltmeter, not across the circuit element. So in this way it is going to give you erroneous values. For that purpose, knowingly we increase the resistance of the voltmeter coil. So always remember that the ammeter is going to have least resistance, whereas the voltmeter is going to have the highest resistance possible. Usually they are in mega ohms, but ideally it should be infinite, but the truth is that it is in terms of mega ohms, but not infinite. Now let us see the extension. Oh, I have written it wrongly as ammeter. Okay, let me change it. Extension of voltmeter range. Okay. So as we were talking about the extension of ammeter range, similarly the same voltmeter which is capable of measuring a low value of voltage can also be modified in a little bit manner so that it will be able to measure a higher voltage. So that is known as extension of the voltmeter range. For example, suppose I am having a voltmeter which is capable of measuring a voltage from 0 to 30 volt, let us say. Okay. Now suppose I want to extend the range of this voltmeter from 0 to 300 volt, then I have to do some sort of modification. So suppose this was the original voltmeter, the maximum full scale voltage reading is 30 volt, and now I want to increase the voltage range to 300 volt maximum. So I can do it very easily. The only thing is that I have to do a little bit modification in the voltmeter. So what type of modification? Here I will connect a very high resistance in series with the voltmeter coil. So when we are talking about the extension of ammeter range, we are connecting a very small resistance in parallel across the ammeter coil. But here, if I want to extend the range of the voltmeter to a higher value, then obviously I will have to connect a resistance, a very high resistance in series with the coil of the voltmeter. So let us see what should be the ideal value of this series resistance which needs to be connected to the voltmeter coil in order to increase its range. Let RC, as usual, let RC is equal to the resistance of the voltmeter coil. Let RS is equal to the resistance of the series coil that we are going to connect. Now V is the full scale voltmeter reading of the original voltmeter. Now Vm is the extended value of the voltage that we want to measure. Now if we want to measure a higher voltage, or if we want to extend the maximum range of the voltmeter, then obviously we have to make some arrangement, and the arrangement is that we will connect the resistance Rs in series with the voltmeter coil. Now just have a look. So it is a little bit complicated. It seems so many diagrams, so many arrows, but it is actually not complicated. Now here I am having the original voltmeter. It was able to measure a voltage of V over here, as you can see. Now if I want to extend the range of this same voltmeter to measure a voltage of Vm, I have connected a resistance RSC over here, you can see. Now how we are going to find the expression for this series resistance? Now just have a look. Before extension, the current that was flowing through this coil of the voltmeter I was equal to the voltage V divided by RC. So here you can see that. Obvious thing, because your current I is going to be the potential difference across the circuit element divided by the resistance of the voltmeter coil. Similarly, if I want to extend the range of the voltmeter, okay, now what happened? Now the total voltage that is available across this circuit element is Vm. But here there is also a change in the resistance of the voltmeter coil. So in this case, after extension, you can see your current I through the voltmeter coil, modified voltmeter coil, is Vm by Rs plus Rc. But remember, in both the cases, the current needs to be the same. Why? Because we have already designed the voltmeter coil in such a way that it can handle only a certain value of current. Therefore, even if we want to modify it or we want to keep it in the original condition, doesn't matter. In both the cases, the current rating is unaltered. So naturally, what is going to happen? These two values or expressions must be same as each other. So if we'll write it in this manner, V by RC is equal to Vm by Rs plus RC. Now we take this V under to this Vm, and we take this denominator up to this point. And if we'll write it, then we are coming or arriving at this particular expression. So extended value of the voltage by the original value of the voltage is equal to 1 plus Rs by Rc. Or if we'll take this one onto the left hand side, then we are left with this much, or finally the equation turns out to be this much. So again, if we will see, then the value of this Rs is, or expression for Rs is given by this expression. So please note it down. We'll solve a problem. Have you noted it?
Noting it, sir.
Okay, note it. Then we'll solve a problem. So today I want to complete this chapter because we don't have much time. Acha, by the way, are you having any holiday next week?
No, sir. Only mid semester.
Yes.
No, sir. Only mid semesters.
So your mid semester is going to start from 16th, right?
Yes, sir.
Okay, if it is going to start from 16th, means it is your Wednesday. So we still have one class in our hand, that is on Monday. So on Monday, we'll try to solve as many as problems possible on this chapter. But today in the lab class, I will be taking your class, I am taking the theory class, and I will try to complete this as far as possible. Okay. Okay, please note down this equation and now solve this problem. So what series resistance is required to make a 1 milliampere 20 ohm meter described above? Means in that previous case, where this much. Please solve it as quickly as possible within 3 minutes. Okay. So now it is 11:27. Let me have a glass of water. I'll come back at 11:30 and I will listen to your answers. Okay. Please do it. Okay. I am back. Have you got the answer? Have you got the answers? I know there will be a little bit of problem.
Sir, it is very
So
big.
it is difficult.
No, sir, very big resistance.
Ah, yes, of course it will be very big. I have already told you because you
Sir,
know in case. Yes,
sir is the
9980.
9980. That is most probably the correct answer. Actually, I have not solved it. Okay, let me solve it. So basically, we are having a voltmeter like this. So this is your voltmeter coil. So this is the original voltmeter. So this is your resistance RC, and it was capable of measuring a voltage, let us say V. Now how much is V? V is equal to I into the resistance of the voltmeter RC. So this is I is 1 milliamps, RC is 20, so ultimately it's 20 millivolt. So this is your original V. You want to extend it, so it is Vm is equal to 10 volt. This is equal to 0.02 volt. Fine. Now what is your RSE? So if you want to extend the range, then it should be connected like this. So this is the resistance. Then you have your coil. So this total voltage that it is capable of measuring is Vm. Please note the diagram. I am doing the diagram. So this diagram will a little bit easier. It may be somewhat easier for you. So this is the actual voltage drop which is going to remain as usual, and across this RSE. So this is your R SE, and this is your RC. So across this it is going to be VM minus V. So RAC is equal to VM minus V divided by V multiplied with RC. So I hope right now you people can do it. So 10 minus 0.02 divided by 0.02 multiplied with 20. Okay, so these two cancels out and it becomes how much? 100 or 1000, sorry, 1000. So this is 9.98 into 1000. So those who have not done it, please do it. So as you people answered correctly, so it is going to be 9980 ohms. So naturally this is going to be a very high resistance, almost equal to 10 kilo ohms. Okay. So this is how, by connecting a 10 kilo ohm resistance in series with a voltmeter, you are actually extending the voltmeter range by almost 500 times. Okay. So everybody have understood? Is there anyone with any sort of doubt? I don't think so. All of you are quite brilliant, intelligent, and I don't think you will be having any problem. Okay, now let us move on. So now let us arrive out at, we'll study about this RC circuit. Before that, before this RC circuit, let me tell you that in engineering, we have different types of circuits. Okay, so we have something known as time variant circuit and time invariant circuit. Okay, so on the basis, or we can say that on the basis of the change or variation of the parameters. So when we are talking about parameters, we actually electrical parameters, the major electrical parameters are voltage, current, charge, power, power factor, phase angle, phase difference, frequency, time. All of these are known as electrical parameters. Okay. Now, there are certain circuits in which some of these electrical parameters vary with respect to time. For example, in case of AC circuit, AC, okay, sinusoidal AC, we have the voltage and current to be time varying. That means the voltage magnitude is going to vary with respect to time. The current magnitude is going to vary with respect to time. Similarly, in case of DC pulsating DC circuit, we also have your voltage and current to be changing with respect to time. So these types of circuit in which your voltage, current are changing with respect to time are known as time variant circuit. Whereas there are also certain circuits in which the voltage current are never going to change for time infinite. That means even if the time is increasing or decreasing, doesn't matter, the parameters are going to remain constant. So such types of circuits are usually known as time invariant circuits. So particularly those who are going for this electrical and electronics engineering, they will be studying in detail about this time variant and time invariant circuit. But right now for your basic syllabus, we don't need to go deeper into it. Just go through this diagram, you can understand it. So first type of circuit is known as time invariant circuit, where the electrical parameters like your voltage and current remains constant with respect to time. For example of such a circuit is a voltage or across a pure resistor or current through a pure resistor. So as you can see here, I am having a circuit which is having a EMF source of 12 volt, and it is connected to a 2 ohm resistor, pure resistor. So if I will measure the current through this conductor, it is always going to show me 6 ampere. Similarly, the voltage drop across the load is going to be 12 volt. So if I'll plot it on a graph, I can say that as the time increases, there is no change in the voltage, neither there is any change in the current associated with the purely resistive circuit. So this type of circuit is known as time invariant. The name itself is saying that it is not going to vary. But there are also certain circuits in which the voltage, current, charge, all these parameters used to change. So these types of circuits are known as time variant circuit. For example, the voltage across a pure capacitor during charging and discharging process. So if in this circuit I am going to have a voltage source or an EMF, and I have, instead of the resistor, I have connected it to a pure capacitor, then already I have told you that suddenly the voltage is not going to increase to 12 volt. It is definitely going to take some time to achieve that maximum voltage. So naturally, the relationship is not going to be a straight line like the previous one, but it is going to vary in an exponential manner like this. Whether it is exponential or in a straight line, we are not concerned about that. The only thing we learn from this graph is that the voltage is actually varying with respect to time. Similarly, the current through this circuit or the charging current is also varying with respect to time. As you can see, it is falling like this. So as the time is increasing, the value of the charging current is decreasing. So such types of circuit is known as a in time variant circuit. So one example of this, already I have told that it is the voltage and current through a pure resistor. Similarly, the current and the voltage across a pure inductor is also going to be a time variant circuit. So in this chapter, we will only talk about the RC time variant circuit. In the next chapter, that is in chapter 27, we will study about the time variant RL circuit. Okay. For RL circuit, the next chapter we will do, but right now we will only concentrate on the RC time variant circuit. And over there, we will learn about this RC circuit, why it is time variant, and how in the charging and discharging process, the charge, voltage, and current are changing with respect to time. So all this stuff we will cover in this chapter. Now, what is an RC circuit? Usually, if a resistance is connected in either series or in parallel across a capacitor, it is known as a RC circuit. So this is a series RC circuit, whereas if I am having a resistor and a capacitor like this, then it is known as a parallel RC circuit. But when we are talking about RC circuit, it can either be a parallel circuit or it may be a series circuit. But in your course, we will only concentrate to this series RC circuit. Okay. Even your parallel RC circuit, they are also very important. Particularly those who will pursue electrical engineering, they will study about this. And even your tube lights or your LED bulbs that you are having in your home makes use of RC circuit to decrease the voltage instead of a transformer. So there are multiple uses of this RC circuit in parallel. We are not concerned about that, just I gave you some idea. Okay. Now, as you can see that your RC circuit are time variant circuits in which voltage, current, and charge, only three parameters are going to vary with respect to time. Now, this is why it is going to change, why the voltage across the RC circuit or why the current through the RC circuit is going to change with respect to time. Now, what is the reason behind it? Now, the reason is something I have already explained when I was explaining you the working principle behind the charging of a capacitor. So this was a capacitor, and when we were charging it, so what I have told you over there, I have told you that when we are going to charge a capacitor by connecting it to a voltage source, now what does this voltage source used to do? The positive terminal is connected to one of the terminals of the capacitor. Similarly, the negative terminal of this capacitor is connected to another terminal of the capacitor. Now, what happens when the positive terminal is connected to one of the conductors of the capacitor? The electrons are dragged to out of this surface and they are forced to be moved through the EMF source and dumped at the other conductor. Now, in the process, suppose for the first time, one of the electron will move and it will get dumped over here. Well and good, there was no problem. The process is going to take place very fast. But when the second electron will try to move in this path, then obviously it will move at a speed. But the problem is that the speed will be slow in comparison to the previous case. Now, why it is so? It is because of the repulsion of the previously present electron over here. Similarly, when I will go for the for the transport of the third charge, the repulsion will be more, and therefore the rate of transfer of charge will be further low. So, in this way, we can say the voltage is going to increase in a gradual manner, whereas the current is going to decrease in a gradual manner. Similarly, the rate or the transfer of charge is also going to increase in a gradual manner. So, in total, I can say it is because of the repulsion between the like charges that the RC circuit is going to behave like a time variant circuit. Okay. Now the opposite thing is going to take place during the charging process. In this case, your voltage is going to decrease gradually, your current is going to increase gradually, and your charge is going to decrease gradually. Just the opposite phenomena will take place during the discharging of the capacitor. Is there any doubt over here? If anybody asks you why your RC circuit is a time variant circuit, tell them or write down very simple, because in case of RC circuit, when electron starts getting assembled at the other conductor because of the inherent repulsive forces between them, the rate of transfer of the charge from the positive conductor to the negative conductor gradually decreases. And because of this, the current decreases as well as the charge deposition is going to increase. Is there any doubt over here? Very important thing. Anyone with any sort of doubt? Hello?
No, sir, no doubt.
Okay, okay. Whenever I am asking anything, whether you have understood or not, please respond me. Otherwise, I cannot ascertain whether my voice is audible or not. Huh? Okay. Now let us move on to the charging of a capacitor. Now let us learn how during a charging of capacitor, the parameters are going to change and it is going to become a time variant circuit. Now here, let me point out one important thing. Over here, I have written something known as caution. Why I have cautioned you? Because I will be using lower cases. So always remember, lower case means time variant parameters. For example, your V DC, in case of DC, I will write V. But in case of time variant or AC circuits, I will write small v. I I will write it in case of AC circuit, DC circuit. In case of time variant or AC circuit, I will write small I. Similarly, regarding this charge Q, I can also make use of this small q. Okay, so only these three parameters are usually written in small cases. Now, so here I am having a RC circuit. Now I am going to charge the capacitor. Now I have already told you why I am going to use a resistance in series with this capacitor during the charging process. One of the girls was asking me this question. I didn't remember her name, but now also I will explain it once again. Now, when this switch is open, I am assuming that this capacitor is completely discharged. So these are the three conditions, sorry, four conditions before. These are the four conditions before starting the capacitor. Now, you have a look at this circuit. Here I am having an EMF source. It is connected to the RC circuit in parallel, and I have a switch. Now the switch is initially open. At time t equal to 0, the switch is open. The capacitor is fully discharged. Since it is fully discharged, your VBC is equal to 0. That is the voltage across the capacitor is equal to 0. The current I is equal to E by R. Now this is not true. The moment I will close the switch, this factor will become true. Now VPC is still equal to 0. That why it is still equal to 0? Because in the beginning, when we are studying about capacitor, in the definition itself, I have told you that a capacitor is a circuit element that opposes a change in voltage. So the moment I will switch on the switch, no doubt the current will start flowing in the circuit, and that current I is going to be equal to E by R. But the problem is the voltage across the capacitor is not going to be suddenly equal to a finite value. Rather, it is going to become equal to 0. Now, why is it so? Because a capacitor is a circuit element which opposes a change in voltage. So, I hope these initial conditions you have understood. Now, the moment I have closed this switch, this circuit is a closed circuit. So current will start flowing. Now, initially what will happen? The current will be maximum. Why it will be maximum? It is because no electron is dumped at the negative terminal. So there is no repulsive force. So the electrons will start moving at a very fast pace. So the initial current is going to be very high. And how much it is going to be high? It is almost going to be equal to E by R. That means the capacitor is almost behaving like a short circuit. That means there is no presence of capacitor in the circuit. It looks like that. Okay. Now, after some time, what will happen? The capacitor will start, or the voltage across the capacitor will start increasing. Why it will increase? Because the transfer of charge has taken place. Now, when the transfer of charge is taking place, there is a development of voltage across the capacitor. Similarly, there will be repulsion of electrons at the negative terminal. So I will start decreasing. So this two things are taking place simultaneously, or rather I will say three things. First one, when I will close the switch, one by one the electrons will start moving, and it will increase the amount of charge on the capacitor. Number one. Number two, as the charges increases on the capacitor conductors, obviously the voltage will start increasing. But at the same time, there will be repulsion of negative electrons on the negative terminal of the capacitors. Therefore, the current will start decreasing. So this is how three things are changing simultaneously when I connected the RC circuit across this voltage source. Is there any doubt? Very important things I am telling you. Try to understand it very nicely. Is there any doubt?
No, sir.
Yes? Tell me. If you are having any doubt, please tell me. Okay. Now, just go through the notes. As the capacitor charges, its voltage VBC, that is the voltage across this capacitor, this capacitor, the voltage is VBC. The voltage across this resistance is VAB. Okay. So as the capacitor charges, its voltage VBC increases and the potential difference across VAB decreases. Why? Because VAB is nothing but I into R and I starts decreasing. But the sum of the total voltage in the circuit is still same. That means VAB plus VBC is still equal to E. So your E is equal to VAB plus VBC. Now your VBC starts increasing, but VAB starts decreasing in such a way that their addition or the sum is always same. Okay. After a long time, what will happen? This VBC will be equal to E and this VAB will be equal to 0. Why? Because the capacitor is now fully charged. There is no current in the circuit. Once the capacitor gets fully charged, then there is no need of any transportation of charge. So the current is going to be equal to 0. So with these conditions, let us mathematically try to find out what is going to be the nature of the change in the voltage, current, and the charge. Okay. So let us go for this derivation. So as I told you that when I will switch on this switch, at time t equal to 0, or at any point of time, if I will add or if I will put KVL in this closed circuit, then what will be the equation? It will be as written over here, E is equal to VAB plus VBC. Now, what is VAB? VAB is nothing but I into R. Similarly, what is VBC? It is nothing but Q by C. And this is equal to 0. Now from this, let us take out this I. So I is equal to E by R minus Q by RC. That means I have taken this IR onto one side and divided the entire LHS and RHS by R. Now since I or the current is equal to the change of the charge or the rate of change of charge, so it is written as dq by dt. So in place of I have replaced it by dq by dt and this is equal to this much. Now this is from here, just take minus 1 by RC as common. If I will do that, then I will get Q minus CE. I have multiplied as C over here divided by C over here. So ultimately your dq by dt comes out to be this much. Now if we will rearrange them in such a way that dq by q is taken under to this denominator position, then the equation turns out to be this much. Now here one important thing is written. We change the integration variable to q dash and t dash. That means in place of this dq or in place of this q and t, I will write q dash and t dash. Why? Because I will use this q and t for the upper limits. The lower limits are still 0 because at time t equal to 0, there was no charge on the capacitor. So q was equal to 0. Now when I will integrate this one, then I will integrate from 0 to q, because as I told you, I have reserved the use of q and t for the upper limits. For that only I made this q dash and t dash. So this is the equation. Now you will integrate, you will get it in this way. Take the anti-logarithm, you will get this equation. Just have a look at these equations. Very simple thing. Okay. Now, initially when the capacitor was completely discharged, Q was equal to 0 and E is equal to IR. Finally, when the capacitor is fully charged, your Q becomes QF and hence I becomes 0. And your QF is nothing but the capacitance into the applied voltage, that is E. So if I will manipulate this equation, then I am ultimately going to get this equation. Okay, so we'll stop the class over here. In the next class, that is in our lab, maybe we'll start it at 2:30 or something like that. But you people please be online by 2 o'clock. Okay, fine.
Yes.
Okay, sir.
Okay, so maybe around 2:30 or 3 o'clock we'll start the class. So, but you people have to be online because I'll start the recording. Otherwise, they're complaining that classes are not going on. So we'll start it at 2 o'clock. But I will start taking the lecture at 2:30 or 3, and I will inform you. Today we'll complete this chapter. Okay.